Hey there, Physics C. So the plan for today is to talk about Ampere's law. Now, I know we've already discussed it in our class period discussions, but what I'm going to do today is go through for you what, a definition for Ampere's law, put it in the context of our other Maxwell equations, give you a few basic examples where we use Ampere's law, and then walk through the derivation for the magnetic field in the center of a solenoid and in the inside of a toroid for you using Ampere's law. So the first thing I want to do is make sure we review Ampere's law so that you can write it, so you know what all the parts indicate, so that you can break it down and understand conceptually what this statement is saying. So notice again we've got this weird looking integral that shows up in here. I've got the integral, and often we use a little circle in here. I know it didn't quite show up on my slide, but the integral around a closed surface of the magnetic field vector dotted with a displacement, a path around which we might say walk or something. And if I take that integral of b dotted with our path length around a closed loop, then that should equal however much current I have enclosed by that loop multiplied by this constant, the permeability of free space. Now that constant, mu naught, our magnetic permeability of free space, that constant is 4 pi times 10 to the negative 7 Tesla meters per amps. So you can always look that value up and grab that value when you need to use that constant of nature. It's a lot like our epsilon naught constant when we're dealing with electric field and the electric permittivity of free space. This current here is a very specific amount of current. That's the amount of current that's enclosed by our Amperian loop. I'm going to draw out a loop. I get to choose what loop I'm dealing with. But that current, how much current I have enclosed, is going to be determining or related to our magnetic field in the vicinity of that wire. We measure our current in amps. Magnetic field is measured in Tesla, and remember that magnetic field quantity is a vector. It has a specified direction. And S is that distance around our Amperian loop. It's basically our path length. If we draw a circle, then we're looking at the circumference of that circle. I mean, if we want, we don't have to use a circle. We could use an Amperian loop that is a rectangle, and I could go around the system with a rectangle, no problem. I would just need to add up the length through which I'm walking all the way around. The one thing, though, that we must do when we're using Ampere's law is it must involve a closed loop. Now, that closed loop doesn't even have to enclose any current. I mean, I could draw my closed loop over here. It doesn't enclose any current. It doesn't allow me to do any simplifications using symmetry in this equation, so it's not really helpful for figuring out what magnetic field is, say, right here. I haven't enclosed any currents. I can't deduce from the current enclosed by that loop anything about the magnetic field. I can't make any simplifications using symmetry. So while this equation is true for any loop that I draw, as long as I am dealing with the current enclosed by that loop, some Amperian loops are going to be more helpful than others in using this formulation and this system to find and to solve for magnetic field. Some systems are just more, applicable. There's some cases where this formula is very much applicable, and there are cases where we have high symmetry. Now remember that Ampere's law is just one of our 4 Maxwell equations that we're working with in electricity and magnetism. This is the one that we use when we want to find magnetic field and we know current. So here we're connecting charge and electricity to the magnetism side. It's our second of our 4 Maxwell equations. We've already talked about our first Maxwell equation, which is Gauss's law of electricity, the integral around a closed surface area of electric field dotted with area vector. So basically looking at our electric flux should equal our charge enclosed by that area divided by epsilon naught. Gauss's law of magnetism, we actually discussed this one a little bit as well. Gauss's law of magnetism is very similar to Gauss's law of electricity, except here we're talking about the magnetic field dotted with an area vector, our magnetic flux. If I take a Gaussian sphere and I enclose some volume with this Gaussian surface, the magnetic flux through that surface should always be zero. Always. Basically, Gauss's law of magnetism tells us there's no magnetic monopoles. And that's our most important piece of information that we can pull from Gauss's law of magnetism. Gauss's law of magnetism says that you can't separate a north end of a magnet from a south end of a magnet. Anytime you cut a magnet in half, you create two new tiny magnets that each have a north and a south end. Ampere's law is our next of our Maxwell equations. And then after this, we'll have just one more Maxwell equation to deal with, and that's Faraday's law of induction. It's quite, an accomplishment here. Maxwell has got his name on these equations that he did not develop, but he found the connection between them. He's most famous for finding this connection between electricity and magnetism. All right, Ampere's law tells us, and it relates to an Amperian loop. So we're going to draw out a path that we're going to use to encircle or enclose some current carrying wire, some charge that's in motion. Our Amperian loop, of course, isn't required to enclose current, but we'll get the most information out if we do enclose some current. So if this is my loop here, so I've got a loop that I've drawn around this wire, and one way I'm going to try to draw this so that it looks a little bit more three-dimensional, because if the wire is going up and down the page, this loop needs to be basically perpendicular to the wire. The plane of the loop should be perpendicular to that wire. And let's assume that we have a radius here for our wire of capital R. And we're going to use Ampere's law. Ampere's law tells us the integral around some closed surface of B dotted with ds equals mu naught times our current enclosed. Now, this time, the right side of our equation, easy. Mu naught times I. That's it. Let's figure out what's happening on the left side of our equation. That's the one with this path integral, and that's the one that often looks pretty scary, but we should be able to simplify it. So the only integral we're really doing is the integral of ds around our loop. That's our goal. Now, let's think about what we know is happening with this current carrying wire. We know that it should be generating a magnetic field around itself. We know that if we use the right-hand rule, we know that we can figure out the direction of the magnetic field. So if I have current that's moving upward, here's what I'd like you to do. Take your right hand and align your thumb with the direction of the current. Okay, so now your thumb should be pointing upward. Your fingertips now, I want you to curl them around, and you're going to curl them in like a circular path around with your thumb pointing in the direction of the current. What you should find is that on the right side of the wire, your fingertips are pointing into the page or into the board. When your fingertips are on the left side of that wire, they're pointing outward towards you. So in the plane of the page, the magnetic field generated by this current carrying wire goes into the page on the right side and out of the page on the left side. Now, if we are right in front of this current carrying wire, like at this position right here, our magnetic field at that position is actually directed to the right side of the page. Again, use your fingertips here and think about the direction that your fingertips are pointing when your thumb is aligned with the current carrying wire and your fingertips are in front of the page. And in the back, behind the wire, our magnetic field points to the left. If I want to simplify this dot product, it would be really nice if ds and b are aligned in the same direction always. If you remember, we used this trick back when we were using Gauss's law for electricity as well. So let's set up ds, our path that we're going to walk through, so that b and ds are aligned with one another. I'd like to walk along this Amperian loop, and I might as well do so that ds aligns always with b. So that means that if I think about starting in front of the wire here, I'm going to move towards the right side of the page. I'm going to follow along this loop. I'm going to go behind the wire, and in the back of the wire, I'm going to be moving towards the left side of the page. I'm going to come forward towards the front here, and then I'm back where I started. The nice thing is if we can align ds and b always as we walk through our Amperian loop, then I can remove this dot product from the equation. I don't need to worry about it at all because ds dotted with b, that cosine theta part, is always going to be equal to 1 because ds and b always have an angle of 0 between them. All right. The next thing I'd like to do is I'd like to be able to say something about b. Hopefully, you can see that this should be symmetric. If I'm a distance of r away from the wire over here versus over here, the magnetic field strength should be the same. Magnetic field shouldn't care if I'm in front of the wire or behind the wire. All that should matter is that I'm a distance r away. That means if I line up my Amperian loop so it is centered on this wire, then the magnetic field at every distance r away should be constant. I should be able to pull b out of that integral. And so now I've got the integral around a closed surface ds equals mu naught times my current enclosed. I know how to do the integral around a closed path ds when my path that I'm walking is a circle of radius r. The integral around that closed surface, b dot ds, that is just going to be 2 pi times r. And so now I have found an equation for the magnetic field strength when I have a current carrying wire, again a long straight current carrying wire, and I'm a distance r away from it. My magnetic field should be equal to mu naught I all over 2 pi times r. We actually saw this equation before. We found this equation when we were using the Biot-Savart law. Now we had to do a much more complicated integral when we were dealing with that. Ampere's law uses symmetry for us to deduce this equation in a much more elegant, much shorter path to that answer. However, Ampere's law has some limitations. We had to make an assumption here to say that b was constant and that this dot product b dot ds is lined up all the way around this loop. The symmetry that we get with the magnetic field being constant really is dependent on this essentially being an infinite line. If I don't have an infinite line, I probably need to use the Biot-Savart law. If those edge effects, like the magnetic field effects when I'm really, really close to the edge or the end of my wire, if those are important, I can't use Ampere's law. It's really only for high symmetry situations. It's also really good, though, for approximating things that aren't infinite. If we don't need to have 100% certainty on, what's happening in the edge effects of a finite wire, then we can use this to get a pretty good understanding of what should be happening with the magnetic field. Next scenario we're going to look at is one where we have a current carrying wire, and we're going to look at the current inside that wire. In fact, let's jump to this. We're going to use Ampere's law to derive the magnetic field at distance r from the center of a wire carrying of radius big R carrying current I naught, where r is less than r. So we are inside of this wire. And in this example, our current is directed into the page. So I flip that on you, so we've got a little bit different perspective now. So if that current is directed into the board, let's figure out what the direction of the magnetic field should be around this, this loop. Okay, so this loop is a distance of r away. That's little r. The radius of the entire system is big R. But if I want to figure out the direction of my magnetic field, here's what you need to do. You're going to take your right hand and you're going to line your thumb up with the direction of the current. So you should be pointing your thumb straight downward at the page or downward at the screen. And you're going to curl your fingertips around in a circle around your thumb. You're going to have your thumb pointing downward towards that current the whole time. Hopefully, what you're seeing is that your fingertips are pointing this way. And they're pointing this way. They're pointing this way as you go around that circle. Over here, they're pointing in that direction. Our magnetic field should be forming a clockwise circle. Remember, our magnetic field lines are always going to be continuous loops, and here they're going to be continuous clockwise loops around this current carrying wire. Our goal here is to figure out how the magnetic field varies as we move outward, but are still inside the wire. We're still going to use Ampere's law. The integral around a closed surface of B dotted with ds is equal to mu naught times our current enclosed. A lot of our assumptions still hold. If we choose an Amperian loop that is centered on our wire, then I should be able to say that the magnetic field is uniform along that loop. There's enough symmetry there that the magnetic field should be a constant. If I pick a path to walk that is parallel at all points in terms of direction with my magnetic field, then B dot ds, that dot product, should simplify. So if I can say that B and ds are always pointing in the same direction, and I can say that B is constant everywhere along that loop, then my integral looks like this. It's pretty good. And now I just need to take the integral around that closed path of ds. I know what that is because this is just a circle of radius little r. So I have B times 2 pi little r equals mu naught times our current enclosed. I still need to figure out my current enclosed though. You see, by taking this segment, this slice of the wire, I haven't enclosed all of the current. I've enclosed a fraction of it. I need to figure out what fraction of the current I've enclosed. That's going to be our next goal. Now, I'm not told what fraction I've enclosed, but I might be able to use the area that I've enclosed as a stand-in for current. So if I want to figure out the current enclosed as a ratio of our total current, that should be the same as the ratio of our area enclosed over the total area. And our area enclosed should be pi r squared, whereas our total area should be pi times big R squared. If I take this ratio and I multiply my total current by that ratio, I'm going to find my current enclosed. So I'm going to sub that in now. Let's go to our next line here. B times 2 pi r equals mu naught times the total current, I0, times little r squared over big R squared, because that's my ratio here. That's the fraction of the initial or total current that I have enclosed. So notice our equation for our magnetic field is equal to mu naught times our total current times R, all divided by 2 pi times the radius of the wire squared. Now this is interesting here, because in this case I have the radius of our loop. So how far out we are away from the center of this current carrying wire, we find that the magnetic field will change as we increase our distance. It seems to increase with radius linearly. What that would look like, because we can graph that now, and I can say that my magnetic field as a function of distance for this current carrying wire should increase linearly. Okay? because inside my current carrying wire, my magnetic field is equal to mu naught I times R all over 2 pi times the radius squared. Once I get outside of that wire, we go back to our formula that we derived earlier. The magnetic field outside of a current carrying wire, mu naught I over 2 pi R. One thing you might want to prove to yourself, check this out, is to make sure that these 2 points are the same. Are they the same? Notice that our magnetic field is going to be the strongest right at the radius, the edge of our current carrying wire. Before that, it increases linearly. After that, it decreases as 1 over R. Now, this assumes constant current density. You actually could have a varying current density. We looked at cases like this when we had charge distributions that were non-uniform. We could do the same thing with non-uniform current density, but you would have to have a function for how the current density changed with radius. That could come up. You may see examples like that, but our approach is still the same. When I'm trying to figure out the magnetic field strength within a current carrying wire, I'm going to this equation. I'm going to Ampere's law. Another place where we can use Ampere's law is with coils of wire. So we're going to take a slightly different look at how we can apply Ampere's law. We're going to look at solenoids, and we're going to look at toroids. All right. Using Ampere's law, we're going to show that the magnetic field inside a solenoid has this magnitude. The magnetic field is equal to mu naught times the current enclosed times little n, where little n is the loops per length. We call that the coil density. All right, if we're going to solve this problem, and so here's our solenoid. So our solenoid is basically a bunch of loops of wire that are stacked together, okay? And we looked at finding the magnetic field inside a single current carrying loop of wire before. We did this with the Biot-Savart law. If I have a single current carrying loop of wire, I should be able to determine the magnetic field right at the center. So in this case, if I have current flowing around this loop, just like that, we have already found from the Biot-Savart law that our magnetic field should point outward. Okay? So now let's take a bunch of these loops and imagine them stacked on top of one another. So we're going to think about this case as if, let's say the magnetic field is going into the board at the top, just like that, and it's pointing out of the board at the bottom, because all of these loops are stacked on top of one another. All right, we're going to use Ampere's law here. If I'm going to use Ampere's law and get something useful out of it, I really want to be able to enclose some current. That's how I'm going to get the best use of this equation. So I need to find a way to enclose current. Now, it looks to me like we can draw a loop like this, and it'll enclose some current carrying wires. So I'll have a net current enclosed. I'm just going to draw a box because I think that's easiest. So I'm going to go from point A to point B to point C to point D. I'm going to go in this direction around this Amperian loop. Notice again my Amperian loop in this case gets to be a rectangle. Let's say that it has a length here and a width. I hope that's okay. And now I want to figure out what's going on here. Now, current enclosed is not so bad. I can actually just count how many wires there are, okay? Because if I have each of these wires piercing through that Amperian loop, then the the amount of current I have enclosed is going to be a multiple of the current carried in a single one of these wires. So if I think about the current flowing through this system away from my battery and into these loops, each of these loops, as that current flows around in this, I guess, slinky-like structure, or spring-like structure, every time I have one of these wires show up right here, I'm going to have a multiple of that current. So for my current enclosed, I've got mu naught times N times the current in a single loop. That side's done, no problem. It's this side here that we want to give a little bit of thought to. So if I want to think about the magnetic field dotted with ds, I'm going to have to use some symmetry to my advantage. The first thing we're going to do is we're going to make an assumption that this solenoid is an ideal solenoid, which means, sort of like we did before with the long current carrying wire, that it's infinite. So we're going to imagine this is an infinitely long solenoid. That's going to allow our calculations to work just a little bit better. But that also means that I'm imagining a scenario in which these loops just keep on going forever and ever and ever and ever. Okay? That has an implication for our magnetic field. If you remember from before, we talked about a single loop. And determining the magnetic field from a single loop. So here's what I want you to do. I want you to take your right hand and you're going to curl your fingertips. So you're going to put your thumb out, so like put your thumb up and curve your fingertips. Sort of like we're going to use this to figure out the direction of our magnetic field. And you want to curl your fingertips so they point downward. At the top of our solenoid. And then you're going to curve them around because underneath our solenoid, they have to point upward. So you're going to curl your hand through a 180-degree turn, and your thumb should be giving the direction of the magnetic field. So if your fingertips are pointing downward at the top of the solenoid and they curl around and they pull upward at the bottom of the solenoid, your thumb should be pointing towards the left-hand side of the screen, or the left-hand side of the page. That's telling us that our magnetic field points this way. Again, we're using the same right-hand rule we did for the Biot-Savart law. Our magnetic field points in the middle of the solenoid towards the left side of the page. Basically, the magnetic field due to each individual loop is just like stacked on top, and so they all add together and they all point right to left across the page. They all go through the middle of the solenoid. But the other thing about this infinite ideal solenoid is there's no spots for the magnetic field to turn and leak outward. Any components of magnetic field that point out in this direction should be canceled due to the symmetry of this system. So I can't actually have any components outside of this solenoid. Our magnetic field is contained completely inside this solenoid. Outside of the solenoid, I should have zero magnetic field. So all of my magnetic field inside the solenoid, all of it directed parallel to the central axis of the solenoid. So let's get back to this integral of B dot ds. It may be easiest for me to break this up into parts. So let's do the integral of B dot ds as we go from A to B. The integral of B dot ds as we go to A to B. Now let's see. The integral of B dot ds when we're going from A to B. And then we'll do the integral of B dot ds when we go from B to C. And we'll add to that the integral of B dot ds when we go from C to D. I'm just going to maybe move this up a little bit. And then we'll do the integral of B dot ds as we go from D to A. Maybe I shouldn't even draw this as a closed loop, because it really isn't. I've broken these up into segments, and they do form a closed loop when I add them all up. But I can also do these integral steps one at a time. All right, so what do I get when I take B dotted with ds along this path from A to B? Well, I do have a path there. I go a length of L along this, this line, but the magnetic field out there is 0. And so what's that mean for B dotted with ds? Well, it means it's also 0. Next part, let's go from B to C. I do have a path that I'm walking along. I've called that path length W. But notice that our ds is pointed directly up the page, and B is pointed perpendicular to it. And so what's B dotted with ds? It's 0. All right, next part, going from C to D. Hey, here I've got magnetic field, and I've got a path length. That one's not 0. That one's going to be B dotted with ds. Well, our path length is L. The angle between B and L is 0. And so that should be B times L. But how about this last segment? If I go from D back to A again, it's actually just like our segment from B to C. Because B and ds are perpendicular to one another, we get 0. And so what I found is the integral from of B dot ds from C to D is all I need to figure out the integral around that closed path. All right, I think we need a little bit more workspace here. So let's sub in. So I know the integral around this closed surface of B dot ds. I can now make a substitution there, because I know that's just B times L. And now I know that B times L, I've already figured this part out, is equal to mu naught n times I. So my magnetic field strength is equal to mu naught times n times current, all divided by the length of our segment, of our Amperian loop. Now, this is one other simplification that we tend to do, and that is, instead of talking about a number of wires enclosed in my Amperian loop, we're going to do this just in terms of properties, measurements that we can take of our solenoid itself. And so we're going to rewrite that. Instead of n over L, we're going to call that our loop density. And so we have B is equal to mu naught times little n, which is our loop density, divided by, or multiplied by I. So the number of loops divided by the length over which those loops occur, that's little n. All right, so that is our equation for the magnetic field strength inside a solenoid. Notice it has no radial dependence that showed up in there at all. Generally, if we are in the middle of that solenoid and we're not near any of the edges, so again, an ideal solenoid we think of as being infinite in length. A real solenoid, probably not infinite in length. But if we had a real solenoid, our magnetic field should be fairly uniform in the middle of in the middle of that solenoid. So a solenoid is one of our most reliable ways to generate a constant, uniform magnetic field. When dealing with electric fields, we also talked about the importance of being able to generate a constant or uniform magnetic field. We did that inside capacitors. So capacitors we could use, again, kind of assuming that they are ideal capacitors, that they are very large surface area compared to the separation distance between the plates. With those assumptions in mind, our electric field should be fairly uniform inside a capacitor, and our magnetic field fairly uniform inside a solenoid. So I have one other example that I wanted to work through, and that is to find the magnetic field around a toroid. Now a toroid, maybe a little bit less known, less likely that you've come across one before, but a fairly common circuit element. And let me tell you what a toroid is. So I've got a picture here showing the currents in a toroid, but not actually a picture of a toroid itself. Here's the way I want you to think about a toroid. Take a solenoid, which is again a long loop of coils, and now turn it around on itself into a donut. And now you have a toroid. So each of these represents a loop, a coil of wire that is now looped around on itself, and they are looping all the way around just like this to make our continuous system, our continuous wire. So if I have a current source here, I should have current that is uniform, constant all the way around this system. We are again going to use Ampere's law. We're going to use the integral around a closed surface of B dotted with ds, and that should equal our magnetic permeability of free space multiplied by our current enclosed. First thing I want you to notice is let's draw an Amperian loop in here. It's symmetric in terms of the distance we are away from each of these current carrying wires. But how much current is enclosed? Well, it's zero. Zero current enclosed. So I've drawn my Amperian loop. I have zero current enclosed. Magnetic field out here, inside here is zero. Let's do another thing. Let's make our Amperian loop all the way out here. First thing I want you to look at, how much current have I got enclosed? Well, notice that each of these currents that are out of the page has a matching current that goes into the page because these are loops and we've sliced through the loops. And so if I have current go out through this loop, it goes back in here, and then it goes out here and back in through here. And so the number of currents out of the page plus the currents into the page should be equal. And so our current enclosed all the way out here is zero, which means our magnetic field all the way out here, also zero. Now we'll look at the interesting one. And that's when we look at the magnetic field inside our toroid. So we're going to enclose some of the currents, but not all of the current. And that's our next step here. So let's think about, again, using our equation for Ampere's law. Let's see. And we'll have to enclose just some of this current. We're going to draw our Amperian loop so that it's in between the inner and outer edge of our toroid. So let's see. Let's draw our Amperian loop right here. You can just imagine that I'm able to draw a circle with a constant radius. Let's call that R. Okay. One thing that you might want to check is what should be the direction of our magnetic field inside this toroid. If this were a solenoid, you would take your hand and you would curl your fingertips around in the direction of motion with the current outward at the top and inward at the bottom. And your thumb should be, let's say that you're lining up your fingertips so they point outward here and inward here. So if you're making a loop where your fingertips point outward at the top and inward at the bottom, you should find that your magnetic field at that point points in that direction. Our magnetic field forms a clockwise loop in this case, clockwise around our toroid. Our best bet is probably to also align ds so that our path around this toroid is in the same direction as B all the way around. So we'll take our path ds all the way around the toroid. And that's going to allow us to simplify this side of the equation. Notice that our current carrying wires are all a constant distance away. So if I'm a constant distance away, I shouldn't be able to tell the difference between this point and this point. They are identical in terms of the symmetry of the situation. Our magnetic field should be the same everywhere at that radial distance r away. So I think we can say that B is constant around our Amperian loop. And then I just need to take the integral around that loop ds. And that should equal our constant, mu naught, times our current enclosed. B here, it needs to be multiplied by 2 pi times r, because that's our path length. And our current enclosed, that one's a little bit tricky. I would need to know how many wires are enclosed here. So I'm just going to call that N. Because I know each of these carries the same uniform amount of current. And if I just know how many wires there are in this toroid, I'm going to multiply that number in there. And now our magnetic field strength, our magnitude of our magnetic field, is just our magnetic permeability times the number of loops times our current times 2 pi r. So this is the magnetic field inside a toroid. It's not the same as our magnetic field inside a solenoid. One thing to note is it actually does depend on our radius. So our magnetic field strength varies as we get further away from the center of our toroid. So if I were to measure my magnetic field strength, say, on this inner surface of the toroid versus my outer surface of the toroid, I would find it gets weaker as we move from one place to another. And it falls off as 1 over r. We can think about what that might look like if we were to graph it. Yeah, let's do a quick graph here. Just over here in the corner, if I'm looking at my magnetic field as a function of r. And notice I have an inner and an outer radius for my toroid. Let's call this A and this B. As we go from A to B, my magnetic field in this region here, 0. As I go from A to B, I'll have magnetic field strength that falls off as 1 over r. And then outside of the toroid, outside of that distance B, it's 0 again. Okay, so kind of, I guess, an unusual looking graph there. All right, I'm going to stop there and give you perhaps a chance to try out some of the homework problems, see how you do. You've now got some great, I hope these are some helpful, pretty good inclusion of all the situations where you might apply Ampere's law. And I hope that helps you out with the homework assignment. Thanks, Physics C.